Okay, so in this video, we're going to be talking about a general rule that we all know, that the derivative of a constant function is equal to 0. We know that for a fact, right? So if we have something like, I don't know, 4x plus 7 over here, and we try to differentiate it, all we're going to get is 4 plus 0, because the differential of a constant in this case is going to be 0. So let's try to write a formal way of expressing that. In addition to that, we're also going to be covering a quadratic polynomial example, which I think is very important if you're trying to determine the gradient at that point, or the instantaneous rate of change, as we talked about in the previous video, right? Okay, so let's start with the derivative of a constant function. How do we express this as a limit is the main question over here. So let's try to do that. So we know for a fact that a constant function is going to look something like this, fx equals c, right? Let's draw a graph over here. We know it's going to be something like this, and it has the same value for all values of x, right? Basically the same y value for all values of x. So that's something we can keep in mind, right? And fx equals c is precisely that. So if you were to try to find the differential at the point, maybe let's call this point P, right? What would that turn out to be? Well, if we try to represent this as we did in the previous video, we get this form, and that's equal to the limit as q approaches a particular number, which in this case is p, right? For f of q minus f of p divided by q minus p. And we know that for a fact, right? Let's try to find the derivative at a particular point. Could we do that though? Think about it for a second. Well, it's kind of giving it away at this point, but I want you guys to consider what happens when you have fx equals c. Does it change for specific values? So if I have f of 1, it's still c. If I have f of 2, it's still c. Let's move on to, I don't know, f of 1 million. Still giving me c, huh? So the idea is that it's going to have the same value. So f of q is equal to f of p in this case. And q is equal to, well, I don't think it would matter at this point, because the value of q and p is basically independent, right? So if we were to rewrite this limit, we'd get q approaching p, 0 minus 0, or basically it's not 0 minus 0 in this case. That's a very specific example. You guys should consider c minus c, because that's a general example. That's for all values of c. C could be 1, c could be 2, c could be 0, as I outlined, right? So basically what we're getting over here is c minus c, right? And we get limit as q approaches p for 0, which is basically just 0 if you think about it for a second. It's nothing more than that at all. It's just simply saying that we're trying to get closer and closer to p, but the function over here is 0, so it won't really matter what's going to happen. It's still going to give me 0. This is how the derivative of a constant function gives me a 0, because what's going to happen is the numerator is always going to give me a 0, because of the fact that a constant function is the same for all values of y. Basically for all values of x. It gives you the same value of y. That's what I'm trying to say. Right. So that was the first part of this video. Let's try to see if we can approach the second part with a little sophistication. Okay. So basically, let's say we have a function, I don't know, fx equals x squared plus x plus 1, right? And we are trying to find the derivative of this function at f dash 1, at basically 1. So using the formulas that we've talked about before, f dash of 1 would simply result in the limit as q is trying to approach what? 1, right? And we have the function f of q, and we have the function f of p, or in this case p is 1, right? Let's just write it over here so that we don't forget. In the denominator, we're basically going to get q minus 1. So let's see if we can get simplifications for this value over here. We know that f of q has to be equal to q squared plus q plus 1, and we know that f of 1 has to be equal to 1 squared plus 1 plus 1. And that's going to give us 3 over here. We know that, right? So what do we get in the numerator over here? Let's just simplify that. Limit as q approaches 1 is going to give me q squared plus q plus 1 minus 3 divided by q minus 1. And if we were to simplify this, what would we get? We'd basically get this. Now, if you guys try to remember, we know how to solve this problem. We've talked about this, right? So if we have something like this, we try to plug in a 1. What's going to happen? We're going to get 1 plus 1 minus 2. And in the denominator, we're going to get 1 minus 1. It's going to give us a 0 over 0. So in these problems, we try to solve the resulting equation using some methods. We try rationalization, but over here, I don't see that being very helpful. We can't just multiply square root over here and make the problem more complicated. But what we could do is maybe factorize the numerator, because it's a q squared term, right? So maybe if we factorize it, q minus 1 might cancel out. So if we have q squared plus q minus 2 over here, and we try to simplify it, we're going to get q squared plus 2q minus q minus 2. And that's basically going to give us q plus 2. At this point, I'm kind of assuming that you guys know how to calculate the roots of a quadratic equation. If you guys don't, it's not really an issue. It could always be looked up online or in the introductory videos that I taught in the very beginning of this course. So let's see what we've got now. Basically, it's q minus 1 times q plus 2 divided by q minus 1. We see that q minus 1 cancels out to q minus 1, and we know why that is. Although it's 0 over 0 form, right? It's of that form, but still it's going to cancel out because it's never exactly equal to 0 over 0. It's very close to it. It's never equal to 0, but it's very close to it. Okay, so what we're getting over here is limit as q approaches 1 for q plus 2. And now we have a very simple term, right? So we're just going to plug in a 1 and we get a 3. So the limit, as we're trying to approach that, gives us 3. So if we were to write this out in a simpler manner, we were trying to find the derivative at the point 1, and we got this. So what I'm saying is, let's try to check that for a second. We know the conventional way of calculating the derivative, right? For x squared plus x plus 1, x squared is going to be differentiated as 2x, and x is going to be differentiated as 1. And then we try to plug in a 1. We get a 2 times 1 plus 1, 3. So this is kind of like a simplification. For people who are not familiar with this right now, the conventional way of calculating the derivative, I'm going to be explaining that in a further video, right? So don't worry about this right now. Maybe you could refer to the next video and understand what's going on. What's important is that you know how to calculate the derivative using this method, because there's a high chance this is going to be tested in the coming examinations, right? So this kind of just shows us that we can calculate the derivative of something like this, right? So yeah, we've covered the two problems we started out with. Hopefully, in the next video, we're just going to talk a little about the different cases that we should know for derivatives. For example, this case, the polynomial case, what happens when you differentiate a polynomial without actually having to do this process, because it's a good idea to have those rules at the back of your mind so that if you get a question like this, you know exactly what kind of answer you want to expect, okay? So hopefully, I'll be seeing you guys in the next video.